Hey everyone, and welcome to the Microsoft Azure Data Fundamentals course. I'm so excited to have you all here, and I hope you're ready to dive into the amazing world of data with me. I'm Krista Santos, your Microsoft Technical Trainer for this course. Over the next few sessions, we're going to break down some super important concepts around data and the Azure services that bring it all together. Now, my main goal for this course is simple. I want you to walk away feeling confident about what data is, how it works, and how you can use Azure to manage it. But don't stress about becoming an expert right now. Today is all about understanding the why and what behind these technologies. Plus, we're going to get hands-on with them so you'll actually see how everything works in real time. We'll kick things off with sessions 1, 2, and 3, where we will break down the core data concepts you need to know, focusing on relational and non-relational data in Azure. Once we've got the core concepts down, we'll move into sessions 4, 5, and 6. This is where we'll dive into large-scale data analytics, real-time analytics, and data visualizations. By the end, you'll have a solid grasp of how to transform raw data into valuable insights. All right. Enough intro. Let's dive into session 1 and kick things off by exploring the fundamentals of data. What is data? Why does it matter so much? And how does Azure come into play when managing it? Let's get started and find out.
All right, let's jump right into some core data concepts by tackling a seemingly simple but big question. What exactly is data? Data is the heart and soul of every information system. It's the fuel that powers everything we do with technology. Whether it's numbers, descriptions, or observations, data is how we capture, store, and make sense of the world around us. But here's the thing. Data isn't just some random collection of facts floating around. It's carefully organized into structures that represent meaningful elements or entities that are crucial to any business or organization. Think of data like a puzzle. Each piece represents an entity. And when you fit those pieces together, you get a complete picture of what's going on in the business. And just like in a puzzle, each entity has specific details that define it. When I say entities, I'm talking about the building blocks of an organization. These could be customers, products, orders, whatever is core to the business. Each entity has attributes, which are characteristics that describe it. For example, if we're talking about a customer, their attributes might include their name, their address, phone number, basically all the details that help us know who they are. Similarly, for an order, you might track the order date, the total amount, the customer who placed it. And hey, without these attributes, working with data would be like trying to put together a puzzle without knowing what the picture is. It's possible, but it's going to take a lot of guesswork. By organizing data into these entities and their attributes, it's like putting together that puzzle. Businesses get a clear, complete view of their operations. This structure allows them to understand how everything fits together, make sense of complex relationships, and make faster and smarter decisions. Now that we've got a handle on what data is, let's talk about the different flavors it comes in. Generally, data can be grouped into 3 main categories: structured, semi-structured, and unstructured. Think of it like organizing your closet. Some things are neatly folded, others are a bit mixed up, and then there's a pile of stuff you're not quite sure what to do with. Structured data is the most organized form of data. It follows a consistent format that makes it easy to store, retrieve, and manage. Think of structured data as a well-organized system where everything is neatly arranged according to a predefined pattern, like a filing cabinet. In this filing cabinet, each drawer represents a different category of information, and within each drawer, folders are labeled clearly, making it simple to find exactly what you need. For example, imagine a filing cabinet in an office where each drawer represents a specific type of record: customers, orders, or products. Within the customer drawer, each folder contains the information of an individual customer, neatly separated by categories like name, address, and phone number. This setup ensures that every piece of information is stored in a predefined format so that when you need to look up the details about a customer, you know exactly where to go and what to expect. Now, say you want to find all orders placed by a specific customer. You'd first pull up the orders drawer and find the relevant folders, which are linked back to the customer's details using a unique identifier, like a customer ID number. The filing cabinet analogy shows how structured data keeps everything neatly organized, allowing you to retrieve information quickly and efficiently. In the digital world, structured data operates just like this filing cabinet. Every bit of data fits into rows and columns, just as it fits into folders. This structure makes it incredibly easy to search, sort, and analyze data with minimal effort. Whether you're handling thousands of customer records or managing inventory for a retail store, the structured approach ensures that everything is in its right place, ready to be accessed when needed. Just like flipping through well-labeled folders in a perfectly arranged filing system. Now let's move on to semi-structured data. Unlike structured data, which fits neatly into predefined rows and columns, semi-structured data doesn't follow a strict format, but still retains some level of organization. Think of it like a filing cabinet where folders aren't always organized the same way, but there's enough structure to find what you need. A great example of semi-structured data is a JSON file, commonly used in web applications. Imagine opening a folder labeled Customers in our filing cabinet. For one customer, the folder might contain their name, 2 phone numbers, and an email address. For another customer, the folder might have a name, a single phone number, while a third folder might be missing a phone number entirely. Despite these differences, everything is still stored in a way that's organized and easy to retrieve. The beauty of semi-structured data is its flexibility. It can adapt to varying amounts of information without needing every record to conform to the same format. This is especially useful in situations where structure of the data is constantly changing. For example, an e-commerce platform might use JSON files to store customer details, product catalogs, and transaction histories. One customer might have several orders and multiple shipping addresses, while another customer might have made only one purchase and provided a single address. In this case, our filing cabinet allows for different folders with different contents, but there's still enough structure to keep things manageable. The adaptability of semi-structured data means it can accommodate both standard fields and optional ones, making it ideal for dynamic environments where data evolves over time. Lastly, we have unstructured data, the most free-form type of data with no predefined format or structure. If we continue with the filing cabinet analogy, imagine you've got a drawer full of random items, loose papers, photos, videos, handwritten notes, and even voice recordings. Nothing fits into neatly labeled folders or follows a standard template, yet each item holds valuable information. Unstructured data can take many forms, such as text documents, emails, images, videos, or audio files. Picture a digital archive filled with product photos, customer reviews, and video testimonials. These may not follow a structured format, but they still provide important insights. For instance, a video testimonial from a customer or a product review can tell you a lot about the customer's satisfaction and preference. Social media posts, email records, and customer support chat logs are also examples of unstructured data. The challenge with unstructured data is that analyzing it requires advanced techniques. For example, to make sense of text-based data like emails or social media comments, we might use natural language processing. Similarly, image recognition technology helps analyze visual content such as photos and videos. While unstructured data is more complex to work with, it often contains a wealth of insights that, when properly analyzed, can drive smarter business decisions. Now that we've explored the different types of data, it's time to dive into how this information is stored. Depending on the type of data, whether it's structured, semi-structured, or unstructured, there are specific storage solutions that are best suited for each. However, there are also versatile storage systems that can accommodate more than one data type. For structured data, one of the simplest storage methods is delimited text files, like CSV files. These files arrange data in rows and columns, making it easier to read and manipulate. For example, an inventory management system might use a CSV file to track product names and prices and stock levels. But as data becomes more complex or grows in volume, CSV files may not be enough. That's when other advanced storage systems come into play. For semi-structured data, JSON is one of the most common formats. JSON is lightweight and easy to use, especially in web applications. For instance, if you're building a web app that collects customer data, JSON would allow you to store this information in a flexible format, supporting different numbers of attributes for each customer. JSON is also commonly used in APIs to exchange data between systems, making it a versatile choice for many modern applications. Another format you might encounter is XML, which is particularly useful in industries that require strict data formatting, such as finance or healthcare. XML allows for hierarchical data storage with tags that describe the data, making it useful for scenarios where data integrity and structure are paramount. For instance, healthcare organizations often use XML to store and transfer patient records between systems, ensuring that data is easily readable across different platforms. Now, when working with large multimedia files such as images, videos, or audio, you'll often use blobs, which stand for binary large objects. Blob storage is specifically designed to handle massive files that can't be easily stored in traditional relational databases. Think of it as a space for all those high-quality videos, photos, or audio files that need to be accessed quickly without sacrificing quality. For example, imagine a video streaming service that stores movies and TV shows. These files would be stored as blobs, allowing the service to deliver content seamlessly while ensuring the data is available in the highest possible quality, even at large scales. Blob storage is like the ultimate digital vault for all those giant media files, ready for fast retrieval whenever you need them. For handling massive datasets, especially in big data environments, optimized formats such as Avro, ORC, and Parquet are your go-to options. Avro is a row-based format, excellent for data serialization and storage, particularly when systems need to exchange data because it includes both the data and its schema. This makes it highly efficient for writing data or serializing it for fast transmission between systems. Parquet, on the other hand, uses a columnar storage format where data is stored in columns instead of rows. This makes Parquet especially powerful for analytical workloads, where you need to query specific columns rather than the entire dataset. Lastly, ORC, or Optimized Row Columnar, is also a columnar format like Parquet, but often provides better compression and faster query performance for specific types of queries. Originally developed for Hadoop, ORC is widely used in big data applications. Next, let's talk about databases, the backbone of data storage. There are two main types of databases, relational and non-relational. Relational databases are ideal for structured data. They organize information into tables, with relationships between tables established using keys. Think about a banking system where every account, transaction, and customer is recorded. Relational databases ensure that all this information stays accurate, consistent, and easy to retrieve. Their structure makes them especially reliable in scenarios where consistency is critical. Now, non-relational databases or NoSQL databases offer much more flexibility. Instead of tables, they store data in various formats, including documents, key value pairs, and graphs. Graph databases are particularly powerful when dealing with highly interconnected data. A great example is a recommendation engine. Think of how streaming services or online retailers suggest movies, music, or products that you might like based on your preferences and behavior. Graph databases map out relationships between users, items, and preferences, making it easier to recommend new content or products based on those connections. Take social media platforms, for instance. Users post text, upload photos, share videos, leave comments, all of which are unstructured or semi-structured data. Non-relational databases excel at handling this kind of varied and interconnected data. When we think about how we use data in everyday systems, it typically falls into two main categories. First, we use data to support real-time operations, where everything needs to happen instantly. Then there is data analysis, where we process and analyze large amounts of data for insights and decision-making. Let's start with real-time operations. This is where OLTP systems or online transaction processing comes into play. These systems are designed to handle fast, high-volume transactions in real time. Think about it. Every time you place an order online, transfer money between accounts, or even book a table at a restaurant, the system needs to instantly update everything from inventory to payment details to availability. That's what OLTP systems are built for, ensuring that transactions happen quickly and accurately. What makes OLTP systems so reliable are the ACID principles, a set of rules that ensure every transaction is handled safely and efficiently, no matter how fast things are moving. Let's break them down. First, there's atomicity. This means that every transaction must be fully completed or not completed at all. Imagine transferring money between two accounts. Both accounts need to update at the same time. If something goes wrong, the entire transaction will fail, preventing any partial updates and ensuring consistency. Next is consistency, which ensures that the database always remains in a valid state. Any changes made by a transaction must follow predefined rules and constraints, so the data is always accurate and trustworthy. Then we have isolation. Even if multiple transactions happen at the same time, they don't interfere with each other. For example, if two users are trying to update the same record simultaneously, the system keeps those transactions separate to avoid any conflicts or errors. Finally, durability guarantees that once a transaction is committed, it's permanent. So even if there's a system crash or power outage, the completed transaction will still be there when the system comes back online. Now let's walk through the process of how operational data moves from raw form to being used in analysis and decision-making. Imagine you're running an e-commerce business. Every day, your systems are collecting data on customer orders, website interactions, and inventory levels. This is operational data, raw, unstructured, and coming in from multiple sources. First, this operational data is extracted, transformed, and loaded into a data lake. The data lake serves as a central hub where all this raw data is collected and stored for future analysis. Next, the data is organized into a schema of tables. This can happen in two ways, either through a Spark-based data lakehouse, where data is stored in files but accessed through tabular abstractions, or in a data warehouse, which uses relational SQL engine to store and manage data in a more structured and table-based format. For example, data about customer purchases, product details, and sales figures can be neatly organized here. Once the data is in tables, it can be aggregated and loaded into an OLAP model or cube, which allows for powerful, efficient analysis. This step is crucial when you want to understand trends over time. For instance, you might analyze how sales in one region compare to another, or how a specific product category has performed over the last year. Finally, whether you're working with files in the data lake, relational tables, or an OLAP cube, all this data can be queried to produce reports and dashboards. These tools give you a real-time view of your business performance, such as customer behavior, top-selling products, and even inventory forecasts. This is the data that helps inform strategic decisions like adjusting marketing campaigns or optimizing stock levels. So let's move into our next lesson in this module: data roles and services. In the data world, there are many roles, each playing a vital part in managing and analyzing data. While we won't cover every role here, like data architects who design the overall architecture of data systems, or data scientists who focus on advanced analytics, we'll focus on three of the most common and essential roles today. First up, we have the database administrators, or DBAs. These professionals are responsible for ensuring databases run smoothly. They monitor performance, manage database security, and ensure proper backups are in place. DBAs are also tasked with managing user permissions and making sure that sensitive data is protected from unauthorized access. For instance, in a financial institution, a DBA might ensure that the customer account data is encrypted and only accessible to authorized personnel, maintaining the highest level of data security. Next, we have data engineers. Data engineers are the builders of the data pipeline. They design, create, and maintain systems that collect, store, and process data. A key responsibility for data engineers is handling the ETL process, which stands for extract, transform, and load. This involves extracting data from various sources, cleaning and transforming it into a usable format, and loading it into databases or data warehouse. For example, a data engineer in healthcare might create a pipeline that extracts patient data from multiple hospitals, standardizes it, and loads it into a centralized database. This ensures that all patient data is ready for analysis and easily accessible. Finally, we have the data analysts. The data analysts play a crucial role in transforming raw data into actionable insights. One of their key responsibilities is data modeling, which involves structuring and organizing data in ways that make it easier to analyze. They also create reports, dashboards, and visualizations that help businesses understand their data. For instance, a data analyst in a marketing department might model customer data to understand which products are performing best among different demographics. Using this analysis, they can help company make more informed decisions about marketing strategies and product development. As we wrap up Module 1, let's briefly touch upon some of the Microsoft Cloud services that can help you manage, store, and analyze data. For operational workloads, we have services such as Azure SQL and Azure Cosmos DB. Azure SQL is a fully managed relational database service that offers high availability and automated backups, keeping your data secure and always accessible. Azure Cosmos DB, on the other hand, is a globally distributed NoSQL database built for high performance and scalability, making it perfect for applications that require fast, real-time data access across multiple regions, especially when dealing with diverse data models. On the analytical side, tools like Microsoft Fabric provide a unified platform for integrating multiple data sources and performing analytics without heavy infrastructure. And for advanced big data processing and machine learning, Azure Databricks offers a collaborative environment that excels at building complex data pipelines and running sophisticated models across large datasets. Of course, this list isn't exhaustive. There are many more powerful tools and resources within the Microsoft Cloud ecosystem, and we'll be diving deeper into those in the upcoming modules.
And with that, we've officially wrapped up session 1. We've covered the basics of data classification, explored different types of storage and workloads, and discussed the key roles involved in data operations. This concludes our session. There are many ways to continue your learning journey. We encourage you to watch other videos in this course or search out your next favorite topic on Microsoft Learn at aka.ms/learn.